Welcome to this Tooldemo screencast. We present a novel scenario-based programming framework for reactive systems with dynamic topology. And we present a method for moving from a scenario-based specification to a scenario-based program implementation. This method is supported by the Scenario Tools tool suite. Software-intensive systems often consist of multiple reactive components that interact to fulfill the system goals. In systems like car-to-car, car-to-infrastructure communication systems, or reconfigurable production systems, the component topology may change at runtime. That is, the component properties and relationships change, which again influences how the components shall interact. Formal scenario-based modeling and analysis based on the scenario modeling language or life sequence charts can help engineers detect design flaws early, and they fit well with how humans conceive and communicate requirements. After modeling the scenario specification, the challenge is to construct a correct implementation from it. We demonstrate the process of modeling and analyzing an SML specification, how we generate a scenario-based program from it, what such a program consists of, and how it can be extended with platform-specific functionality that was not subject of the specification. We also demonstrate how SBP programs can be executed in a distributed system, communicating via the MQTT protocol. As an example, we consider a car-to-X system that coordinates cars passing through a narrow passage created by an obstacle. The two endpoints mark the position of the obstacle. There are parameters around each endpoint that, when a car passes them, represent the events of approaching the obstacle, reaching the obstacle, and entering the narrow passage. Consider the following two scenario-based requirements. First, when a car approaches the obstacle controller must allow or disallow the car to enter the narrow passage before the car reaches the obstacle. Second, when a car approaches the obstacle, it must register at the obstacle controller. Then the controller must check whether another car is already registered for passing the obstacle. If so, the obstacle controller must add the approaching car to a waiting list and disallow it from entering. Otherwise, it must register the car for passage and allow it to enter. Let us take a look at the SML specification of the system. An SML specification refers to a domain class model that defines system and environment components and their properties and relationships. In this case, it defines the classes for cars, obstacle controllers, and coordinate processors. A coordinate processor is a component that abstracts from the car's positioning sensors and is the source of the before-mentioned position events. The specification defines which components are system components by listing their classes in a controllable section. Here, cars and the obstacle controllers are system components, coordinate processors are environment components. The specification mainly consists of scenarios, of which there are two kinds. There are assumption scenarios that describe what the environment will or will not do, and there are guarantee scenarios that describe what the system may, must or must not do in response to environment events. The scenarios are organized into collaborations which define roles that represent components in the system. The scenarios refer to these roles in messages and conditions. Let us take a look at the second scenario called car registers at obstacle. It is initialized by the message approaching obstacle sent by the coordinate processor. Next, the car must register at the obstacle controller. The message has two modalities. Urgent means that the message must occur before the next environment event occurs, and strict means that at this point the order of messages as specified by the scenario must not be violated. That is, no message appearing only at another point in the scenario must happen at that point. For example, the enter allowed message, which must occur only later. Next, there is the alternative. If no car is currently registered at the obstacle controller for passing the obstacle, that car must be registered for passing, and the obstacle controller must allow the car to enter the narrow passage. Otherwise, the car must be added to a waiting list, and the obstacle controller must disallow the car to enter the narrow passage. We can automatically check the specification for realizability. The procedure checks whether there is a strategy for the system so that for any environment behavior, the system can guarantee that the specification will be satisfied. It turns out that the specification is realizable. Moreover, all explored states are winning states. Without going into the details, this is a condition that must be satisfied if we want to generate SBP code from the specification. Let us assume that we actually forgot to include the assumption that the cars will obey the entering disallowed messages by the obstacle controller. Then, when rerunning the check, it actually reports the unrealizability of the specification. This is because crashes can occur when we do not include the assumption. After fixing the specification again, we can generate an SBP program from the SML specification. SBP extends BPJ, the behavioral programming framework for Java. BPJ programs consist of so-called B threads that coordinate the execution via calls to a special bsync function. B threads yield at bsync calls, where they can request, wait for, or block events. Then an event that is requested but not blocked is selected, and all B threads that requested or waited for that event will be notified. These B threads then resume execution and the process is repeated. SBP code mainly consists of special scenario B threads that correspond to and can be generated from SML scenarios. The SBP framework provides additional B threads that adapt BPJ to reflect the execution semantics for SML. Let us look at the generated scenario car registers at obstacle. A scenario extends a set of operations of an abstract scenario superclass. In the initialization method, a scenario defines one or more initializing messages. Upon the occurrence of a matching message event, a new instance of the thread will be started. Then register alphabet will be called, where the scenario defines all messages appearing in the scenario. Register role bindings computes dynamic role bindings sensitive to the topological context in which the initializing message event occurred. The body method represents the scenario body after the initial message. Here we see how the strict and urgent register message is translated into a function call that leads to requesting the event in the underlying BPJ event selection mechanism. Next, we demonstrate the distributed execution of the SBP code. We execute a test run where external events effectively come in the form of GPS coordinates. A platform-specific coordinate processor implementation translates them into specification-level events. For testing purposes, GPS sensor values come from mock sensors that emit them in a time-scripted sequence. For demo purposes, we simulate the components on one local machine, but as separate processes that communicate over a network. After starting the setup, we see three windows, two for cars A and B and one for the obstacle controller. The car windows visualize dashboard messages that would be shown to the drivers. Here car A arrives at the obstacle before car B. Car A can go while car B must stop. Now car A passes the narrow passage. Once car A clears the narrow passage, car B is allowed to go. We are also able to execute SBP programs on Android phones, which can act as GPS sensors and dashboards. This way we can execute the application when driving in real cars. To summarize, in this tool demo we demonstrated a method for moving from scenario-based specifications to scenario-based program implementations. In particular, we presented SBP, a new scenario-based programming framework. We implemented the first proof-of-concept distributed execution technique. This technique, however, must yet be improved, for example to make network communication more efficient and to allow components to work with only partial views on the global component topology.